Oscilloscopes have long been the tool engineers relied on for debugging problems in their designs and analyzing signals in their systems. The first oscilloscopes were analog and did a great job of accurately displaying the signal being probed directly on the display. These oscilloscopes, although providing tremendous insight into electrical systems, came with some limitations. For example, it was not easy to make measurements on the signal or save any results or findings. As digital oscilloscopes were developed, the user had access to a new set of tools for debugging problems. New digital oscilloscopes sampled incoming waveforms and recreated them on the display. The digital waveforms could be analyzed with a wide variety of mathematical and measurement tools. Waveform data could be saved and manipulated, providing tremendous insight in the system being tested. Modern oscilloscopes have a few key banner specifications: bandwidth, sample rate, and record length. For years, oscilloscope manufacturers have developed innovative technology to improve all three of these key specifications, allowing engineers to capture higher frequency signals at faster rates and for longer periods of time. But for too long, one key banner specification has been overlooked: ADC Resolution. In a digital oscilloscope, the resolution of the instrument comes from the resolution of the analog to digital converter, known as an ADC, used in the acquisition system. Today's typical benchtop oscilloscopes have an 8-bit ADC, which digitizes signals using 256 quantization levels. Before thinking about the resolution of an oscilloscope, it is important to understand what resolution really means. Resolution is defined as the ability of a device to reproduce fine detail. Resolution specifications can be found in a wide variety of consumer electronics. Remember the first time that you ever watched a sporting event or movie on a high-definition TV? The amount of detail you could see was amazing. The people, scenery, and colors were crisp and like nothing you had seen from a television before. This beautiful display on a full HD 1080p television comes from a 6 times improvement in resolution over standard televisions. The ability to reproduce fine detail and display crisp waveforms would bring tremendous value to an oscilloscope, but traditionally, only 8-bit ADCs have been used. In 2011, Teledyne LeCroy introduced the first high-resolution oscilloscope, delivering 16 times more resolution than that of an 8-bit instrument. Oscilloscope resolution comes from the resolution of the ADC, which has 2 to the nth bits of resolution. In an 8-bit system, 2 to the 8th resolution means 256 quantization levels. A 12-bit oscilloscope has 2 to the 12th resolution, or 4096 quantization levels, an improvement of 16 times. This additional resolution enables 12-bit oscilloscopes to display waveforms that are more precise and show more details. This basic example of a thermometer can be used to understand quantization levels and their impact on measurements and measurement precision. On the right side of the thermometer, temperatures are displayed in 10-degree increments. On the left, in 1-degree increments. These increments can represent the quantization levels of an ADC. The left side has 10 times more quantization levels, or 10 times more resolution, meaning the temperature can be read as precisely as 1 degree. Looking only on the lower resolution scale, the temperature just appears to be close to 0 degrees and cannot be measured precisely. The full benefit of a 12-bit ADC cannot be realized by just changing the ADC. A completely new approach to oscilloscope design is required. Teledyne LeCroy's HD4096 technology combines high sample rate 12-bit ADCs with high signal-to-noise ratio input amplifiers and a low-noise system architecture, providing 16 times more resolution for oscilloscopes up to 1 GHz of bandwidth. These 3 components of HD4096 technology combine to give the user of a high-definition oscilloscope the ability to display crisp, clean waveforms, see more waveform details, and make measurements with unmatched precision. The benefits of HD4096 technology can be clearly seen even when looking at the most basic waveforms. Here, a basic pulse was captured on an 8-bit oscilloscope. Compare it to the same pulse from an oscilloscope with 12-bit HD4096 technology. The waveforms are thinner, cleaner, and crisper. Here is a similar comparison with a simple ramp. First captured on an 8-bit oscilloscope, then captured on the 12-bit high-definition oscilloscope. Lastly, this sine wave was captured on an 8-bit oscilloscope, and compared to the same sine wave captured on a 12-bit high-definition oscilloscope. Beyond crisper, cleaner waveforms, HD4096 technology enables the oscilloscope to display more signal details. Here, a waveform with ripple is captured by both an 8-bit oscilloscope and a 12-bit HDO. It looks like there may be some ripple on the 8-bit waveform, but zooming in only shows noise. Zooming into the 12-bit waveform clearly shows the ripple. This is a signal detail the user has never been able to quantify or even see before. HD4096 technology also improves measurement precision. The peak-to-peak measurement of this signal is displayed as 165 millivolts by the 8-bit oscilloscope. The same measurement on the same signal captured by the 12-bit high-definition oscilloscope is displayed at 134 millivolts. Teledyne LeCroy's high-definition oscilloscopes with HD4096 technology provide 12-bit resolution at 2.5 gigasamples per second with up to 15 bits using enhanced resolution mode. Models are available with bandwidths from 200 MHz to 1 GHz and long memory up to 250 megapoints per channel. Each model features a large 12.1-inch touchscreen display. Beyond high-performance hardware, the high-definition oscilloscopes provide a comprehensive set of debug, analysis, and problem-solving tools that provide tremendous insight and shorten debug time.